Here we go. All right, so when we're talking about time harmonic signals on transmission lines, what we have is the same thing that when we talked about plane waves we have waves that have this form. What a great time for my marker to stop deciding to work. We have waves that are of the form cosine of omega t minus kz for a wave that's going in the plus z direction. Or omega t plus kz for something that's going in the minus z direction. And obviously you could replace z with x or y for waves that are going in the plus or minus x and y directions too. And a wave that's like this, it might have a cosine or it might have a sine, that's fine too. These have different phases, or you could switch the sine and the cosine, or you could just add some constant phase shift to them if you have something that's in between the phase of a cosine and the phase of a sine. Anyway, you can have all these different things. And we can also talk about them in the phasor domain. Where having some amplitude cosine of omega t minus kz plus some phase is equivalent in the phasor domain to a e to the minus j kz. I need a parentheses there. kz plus phi, like that. And as you know, when you're doing phasor notation, the e to the j omega t is implied. So there's like a ghost of an e to the j omega t here. And if you want to convert this back, well, if you want to convert that back into the time domain, you multiply by this ghostly e to the j omega t, and then you take the real part, and that gets you back into the time domain. We're going to do some stuff using phasor domain today, so I wanted to mention that. If you are not clear on why this stuff works, review Euler's identity. I think early in the semester, I put up some review materials about phasor notation. There's a good Khan Academy discussion of it. So watch that video and that'll help you out a lot. Okay, but here's the thing. When you have a wave that is like that, cosine of omega t minus kz plus phi. And let's say that that is some voltage, right? A voltage as a function of time is equal to that. Then if I were to draw the plot of voltage as a function of position, it might look like this. At some time, t equals t1. But if I allow time to advance, then the wave stays the same shape, but moves forward in z like this. And this might be at t equals t2. The reason that this happens is because at, let's say, this location on the wave, or this location on the wave, this argument of the cosine is the same value. But since t has increased, right? So t over here has increased. We need a corresponding increase in z to cancel out the increase in t so that this value that produces that maximum of the out of the cosine stays at a constant argument value, right? Constant value for the same point on the wave. And then this particular point on the wave moves along as time advances. The distance that it moves, if I were to write down like delta z, that would just be t2 minus t1 times omega divided by k. But since omega is 2 pi times the frequency and k is omega square root mu epsilon, which is also equal to omega divided by the phase velocity, this omega divided by k here is actually just t2 minus t1 times the phase velocity. Where, as a reminder, we talked about this when we were talking about plane waves, but the phase velocity is 1 over the square root of mu times epsilon. And if you are in free space, the phase velocity is equal to c, the speed of light, which is 1 over the square root of mu naught times epsilon naught. For transmission lines, I want to make a note here. For transmission lines, your book uses the Greek letter beta for the phase constant instead of k. K is known as the wave number, which is sort of a property of a medium that a wave propagates in, and it is usually for plane waves. Beta is sort of a more general thing called the phase constant, which in more advanced settings can be a different value from k in a particular medium, depending on what types of waves are allowed to exist. So for transmission lines, we'll be using beta, but it works the same as k. It is the phase constant, and that's kind of the important thing that you got to do. So I'm going to start by having you do an activity here. If you are given that the voltage as a function of time is equal to cosine of omega t minus kz plus phi, like we just did, what I'd like you to do, step one, is draw a plot. I'll just write down plot. The voltage as a function of time at some fixed z value. And then the question here is, what is its period? That one is kind of a softball, probably won't be too hard. Part two is plot the same voltage, and really this should be written as V of ZT because it's a function of both things. Plot the voltage as a function of position at a fixed time. And then I want you to figure out what is its spatial period. Which is otherwise known as the wavelength. So at this point, I will pause the recording and ask you to go into your breakout rooms and do this activity, draw some graphs. Shouldn't take too long, maybe 5 or 6 minutes for this, and then I will bring everyone back. So my recording is back on now. Welcome back from the activity. We were plotting voltage as a function of time for a fixed position and a function of position for a fixed time. So those two plots actually look pretty much the same because it's really just a cosine, right? And the period, if you're plotting it versus time, that period is 2 pi over omega, or 1 over the frequency, if this is time and this is voltage. If you plot the same wave as a function of position for a fixed time, what you get is the same sort of shape, but obviously this period is not going to be 1 over omega because that doesn't even have the right dimensions. Sorry, it wouldn't be 2 pi over omega. That doesn't have the right dimensions even. Omega is radians per second. And if you divide 2 pi by something in radians per second, you'll get seconds, not distance. So here, what we actually need to do is 2 pi over k. Because k is the wave number. It has units of 1 over meters. And if you remember in the argument, cosine of omega t minus kz, k is multiplied by z in exactly the same way as omega is multiplied by t. So the spatial period, heavy air quotes, I'm doing air quotes right now. There, now you can see. The spatial period of this thing is 2 pi over k, which we define to be the wavelength and use the symbol lowercase lambda. Side note about lambda, the way to write a lambda is like this, like one swipe going from top left to bottom right, and then another swipe this way. It's not an upside down Y, but often if I need to like write down a Greek letter real quick on a computer in any way, the best way is to use Wikipedia to the best way is to use Wikipedia to look it up and then copy and paste the Greek letter into whatever I'm writing. So anyway, that's the thing. This wave now has time variation, which is defined by the period and the frequency. And it has, that's pretty glary. And it has this variation with position, which is defined by the wave number and the wavelength. Why are wavelengths important? Well, what we will find today, and what we sort of implied last time, is that voltage and current obey wave equations just like electric and magnetic fields do. Which means that actually, in fact, the voltage everywhere on a wire is not constant if you have non-zero frequency, if you're not at DC. You know, for time varying, not DC circuits, not even circuits, but signals. The voltage is not constant on a wire or on a node. This can be very upsetting if you try to design something as though voltage does behave that way and then it doesn't behave that way. The reason that we haven't talked about this before is that this question of wavelength, right? The wavelength is the speed of light divided by the frequency. There are all these relationships between wavelengths. Like, remember that the speed of light is omega divided by k, but k is 2 pi over the wavelength. And so if you've got 2 pi over the wavelength and 2 pi over frequency, then you end up, anyway, it turns out like this. There are all these different relationships. But if you are working at low frequencies, like at 60 hertz, right? If you put in, then the wavelength is 3 times 10 to the 8th. 3 times 10 to the 8th meters per second is the speed of light, divided by 60 hertz. Remember, hertz are 1 over seconds. So that turns out to be about like 5,000 kilometers. So we don't care about this. This is a big circuit. We would have to have a really, really big circuit to care about the size of a wavelength here. because usually transmission line effects start to matter when the circuit size is about 1/10 of a wavelength. But let's take a look at what happens at 10 gigahertz. In that case, if we do the same thing, the wavelength is 3 times 10 to the 8 meters per second. And the frequency is 10 times 10 to the 9th hertz. So then that wavelength at 10 gigahertz, so 10 gigahertz like that, is 3 centimeters. Oh, all of a second we really, really care because many circuits, in fact, most circuits that I have ever worked on or seen are larger than that, especially everything you've done in every class, right? Have you ever made a circuit that was smaller than 3 centimeters, excluding like semiconductor devices, if anybody was in that class? You haven't. That's why we haven't talked about it yet. So voltage and current have a wavelength, and their amplitude varies with position according to the wavelength. But if you are at a low enough frequency that the wavelength is really long, then we don't care about it. But if we're at a high frequency where the wavelength is short, then we do. These are sort of, when you're at a low enough frequency or the circuit is small enough, this is something that we in electromagnetics refer to as the quasi-static approximation, meaning that we're not quite at DC, but we're almost at DC and it's close enough, like the wavelength is short enough or the pieces are electrically small enough that we don't care about it. Let's talk for a minute about why transmission lines support waves. Consider a short transmission line section. We have a short transmission line section here, and it's got length delta L. And as we have discussed in our earlier chapters, this structure has some capacitance per unit length, right? It has a per unit length capacitance, which I'm going to name C prime, and a per unit length inductance, L prime. And it has length delta L. And let's say that delta L is really short, so we can treat this as though these are lumped quantities. And so this circuit is approximately equivalent to an inductor and a capacitor connected like this. And I have said that voltage is a function of position and time. We're going to work in the phasor domain for this. So I'm just going to write down everything in terms of Z. So at this end, we have voltage V of Z and current I of Z. And over here at this end, we've got current I of Z plus delta Z and voltage, oh, sorry, not delta Z, delta L, and voltage V of Z plus delta L. The value of this inductor is the inductance per unit length times delta L. And the value of this capacitor is the capacitance per unit length times delta L, because that's what per unit length means. Now, if I write down Kirchhoff's voltage law around this circuit, I have a voltage rise across V of Z. I have some voltage drop across the inductor, and then I have another voltage drop across V of Z plus delta L. So I can write that V of Z is equal to J omega L prime delta L I of Z plus V of Z plus delta L. I also write down, that was KVL, Kirchhoff's voltage law. I can also write down Kirchhoff's current law, KCL, which I'm going to write for this node right here where the capacitor is attached. The current coming in and going through this inductor is I of Z. And there are two pathways through which it can leave this node. It can leave through I of Z plus delta L, or it can go through that capacitor. The current through the capacitor is J omega C prime delta L V of Z plus delta L. And then over here we have the other one, I of Z plus delta L. Does anybody remember the definition of a derivative, like the limit definition? Fundamentally, the derivative of something, like d, if you have some function of x, df dx, like that, is f of x plus delta x minus f of x divided by delta x. And then you take the limit of the whole thing as delta x goes to 0. That's what we're going to do here. We're going to subtract these voltage terms to get them on the same side and divide the whole thing by delta L. And then we're going to do the same thing with the current. And then we're going to take the limit of both of these equations as delta L goes to 0. So here what I've got is the limit as delta L goes to 0 of V of Z minus V of Z plus delta L divided by delta L. So I've swapped this order here. So this is going to be a negative derivative. It'll work out fine in the end. Is equal to J omega L prime I of Z. And for KCL, I get the limit as, whoop, I need a little more space at the bottom here. Limit as delta L goes to 0 of I of Z minus I of Z plus delta L divided by delta L equals J omega C prime. This is V of Z plus delta L, but since we're taking the limit as delta L goes to 0, I can write V of Z here, and that's fine. Well, these are both derivatives, right? So if I replace those two things by minus dV dz over here and minus di dz over here, these are sort of the transmission line version of Ampere's law and Faraday's law. Because remember, these j omegas are time derivatives, and these are position derivatives. And when you have a pair of coupled equations where there's time derivatives and position derivatives involved with two different variables, what comes out tends to be a wave equation. And that's going to be what happens here too. This pair of equations is actually very important and has a name. It is called the telegrapher's equations. And it's called that because this little piece of math right here is what enabled the invention and operation of the telegram over long distances. Without it, it was kind of impossible to understand how telegrams worked and how, like, because again, we're talking about the wavelength, right, being really long. So if you want a long distance telegram, those wires have to be many kilometers long. These telegrapher's equations here were the thing that describes how voltage and current behave on those really, really long transmission lines that connected telegrams from one place to another. So to get a wave equation out of this, though, here's what we do. Take another z derivative up here, and then we're going to substitute in, well, we're going to end up with a di dz over here, and we're going to replace it with this stuff. So then, if we do that, we end up with the second derivative of the voltage with respect to z plus omega squared L prime C prime V is equal to 0. A wave equation, because again, this is a second derivative with respect to time. In phasor domain, multiplying by j omega gets you that. So much like the electric and magnetic fields, voltage and current on a transmission line obey a wave equation, because as you might imagine, if I just took that z derivative of the lower equation instead of the top equation, we could write the same equation for I as well. In fact, even cooler stuff, on a transmission line, omega times square root of L prime C prime is equal to omega square root mu epsilon. And so transmission lines have the same wavelength and phase velocity as plane waves do. When they're filled with the same materials. All right. So we talked about how the current is not the thing that is carrying the power, right? It's not the conduction of individual charges from the source to the load. And what is really carrying the energy in the transmission line is that electric and magnetic field wave. The way that it carries that energy is with something called the Poynting vector. The Poynting vector has a really fortunate name. Obviously, it's named after some person named Poynting, but it actually does point. It points in the direction of current flow, not current flow, of power flow. So for an electromagnetic wave, the Poynting vector, for which we use the variable capital S as a function of time, is the cross product of the electric field and the magnetic field. This means that if these are time harmonic, this is a cosine at some frequency omega, this is a cosine at some other frequency omega, this is going to have frequency, it's going to have a DC part, and then it's also going to have a frequency of 2 times omega. If you want to talk about the time average power flow, which is usually what we care about as engineers. Oh, and this is a vector, so it has magnitude and direction. And it has units of watts per meter squared. So it's a power density, meaning that you could like do a flux integral of this to find the power leaving some area, some volume. Anyway, in the phasor domain, we can't get the time varying Poynting vector, but the double frequency part of it isn't all that informative anyway. Usually what we care about as engineers is the time average pointing vector. And that in phasor domain is 1/2. I'm going to write this as E squiggle to show that it's a phasor cross H squiggle complex conjugate. Those are phasors. So on your transmission line here, your electric field tends to point this way. Your magnetic field usually points in between the wires, right? So doing the grab the wire trick, the magnetic field might be into the board here. And if you figure out E cross H, E cross H, then your pointing vector is going to be that way. Let's go back and talk about the wave equation, right? So this tells you that there are waves carrying power in this direction. If you had current flowing this way, the direction of the magnetic field would flip. It would be out of the board instead of into the board, or the other way around. Anyway, and then you would have power flowing the other way. Why does that matter? Because that wave equation we talked about admits solutions that look like this. Voltage as a function of position is equal to some amplitude times e to the minus j beta z. This is a forward going, because it's going towards positive z, plus some other amplitude times e to the plus j beta z. This is backwards, not in any sort of non-physical or electromagnetically exotic sense, but just in the sense that is going towards minus z, while this one goes towards plus z. And those are the solutions that you have. And beta, like I said before, is equal to omega square root of L prime C prime, which is equal to omega square root mu epsilon. Current does the same thing. The solutions for this are that amplitude divided by the characteristic impedance, which we remember from Monday, e to the minus j beta z, minus, because the current goes in the other direction for the minus going wave, b divided by z naught, e to the plus j beta z. Remember we talked about reflections? If you have a forward going voltage wave with some amplitude, like let's say V naught, like let's say that we have a forward going one that we're going to call V plus of Z, that is V naught e to the minus j beta Z, and it is going down some transmission line terminated by some load, then you're also going to have a minus going voltage wave going back the other way. And that minus going voltage wave is going to look like reflection coefficient at the load times V naught times e to the plus j beta z. So your total voltage as a function of position is going to be V naught times e to the minus j beta z plus gamma L e to the plus j beta z, like that. Okay, and gamma L, just like it was before, is the load impedance minus the characteristic impedance divided by the sum of those two things. Take a look at this though. These things have different phases. This one accumulates phase going to the right. This one accumulates phase going to the left. So there are going to be regions of constructive and destructive interference on here, a standing wave. Also, this one carries some amount of energy going to the right, and this one carries some amount of energy going to the left. So there's going to be some net amount of, sorry, when I say energy, I mean power there. there's going to be some net amount of power that goes to the right, and some amount that is reflected back and doesn't really go anywhere. It's important to note that we're still in phasor domain. All of these terms still have that invisible e to the j omega t on them. So although what this does is it sets up a standing wave, like v of z has some amplitude that's now going to sort of look like that. That standing wave still varies with time. It's all got e to the j omega t attached. So it's going to, this is like the amplitude. So it might be v of z and then actually have like cosine of omega t like that on it. So it's still going to pass through zero, become negative, become positive again. It's going to oscillate like this amplitude profile along position is multiplied by a cosine. If I use my knowledge of Euler's identity to break this up, I can write this as V naught times, right? This is 1 times e to the minus j beta z, but I can write it as 1 minus gamma plus gamma e to the minus j beta z. So then I can have 2 gamma L cosine of beta z plus 1 minus gamma L e to the minus j beta z. Now it's really explicit. This one is made up of equal parts of waves that are propagating to the right and to the left. No net power is carried by this thing. This is the standing wave. And then there's this bit that actually is still carrying power that way. If I were to plot this, I'm kind of going through this fast because the activity that I want you to do about this is to plot it yourself. So pay attention here. And I wanted to know that amplitude. It would look like this. There would be some maximum voltage, some minimum voltage, some average voltage in the middle, and it would kind of look like a cosine. And like if my load is here, the distance that I am from the load would determine whether I see this V max or this V min. The max voltage value is 1 plus the absolute value of the load reflection coefficient. The minimum voltage value is 1 minus the absolute value of the load reflection coefficient. Remember that magnitude gamma is less than or equal to 1. And so you have a standing wave that looks like this. A metric that we often use when we're talking about transmission lines circuits is the voltage standing wave ratio, abbreviated VSWR, sometimes pronounced VISWAR, despite my strenuous objections. I think it sounds stupid, but it's pretty much industry standard to say it that way. Sometimes people also write SWR for standing wave ratio because the current has a similar standing wave, so it's not specific to voltage. But anyway, I think they typically measure voltage back in the day when this was a way that people measured transmission line circuits, so they still refer to VISWAR. And it's 1 plus magnitude gamma divided by 1 minus magnitude gamma, or the max voltage divided by the minimum voltage. Makes sense why you would call it the voltage standing wave ratio now, because it's the ratio of the voltages in the standing wave. Important thing to note, for complex loads, the reflection coefficient here can also have a phase. It's not just positive or negative. So if you have something that has a capacitor or an inductor on it, that can shift the position of these voltage maxima or minima. But if you don't change the magnitude of gamma, it doesn't change the VISWAR. So there you go. Second activity, last thing for the day. This is the thing I want you to take a screenshot of. So pay close attention. Draw the voltage standing wave. for characteristic impedance is 50 ohms. And the load impedance is 0 ohms, a short circuit. That might take you the whole rest of the time, or if you're really on top of things, you can also try with a different load impedance, ZL equals 25 plus J25 ohms. In both of these cases, you should start by finding the load reflection coefficient and the voltage standing wave ratio, and then you can use this equation to figure out what is the phase, I guess, or whether you're at a low, where you are on the voltage standing wave, maximum, minimum, neither, kind of in the middle, at the load, and then sort of draw the shape of the standing wave from there. I'm going to reopen your breakout room and let you try that out. All right, welcome back. I want to just quickly tell you a few takeaways from that activity, right? If I write down voltage as a function of Z is equal to V naught, I factor out e to the minus j beta Z, so then I have 1 plus, in the first example, gamma was equal to -1, and then I have e to the 2j beta Z, like that. Oh, you can't quite see that. There we go. Start to write straight. Take a look at this. When the value of Z is 0, I have a negative number and a positive number added together. So this is going to turn out to be a voltage minimum. And I will get 0 in this case because the magnitude of gamma is 1. Implicitly, the way that we defined this, Z equals 0 at the load. So I have a voltage minimum here. Then you can see that if I go some distance so that this argument is pi, is j pi, then I have -1 times -1, which gets me a positive number. And then I get to the maximum value, which is 2 V naught. Like that. And I can keep going. And if I'm plotting the absolute value of V of Z, then I get a standing wave that looks like this. This distance is not one wavelength. It's actually half of a wavelength because of this factor of 2 right here. You can think of that as meaning that the forward going wave accumulates phase as 2 pi in one wavelength. The minus going wave accumulates pi this way as 2 pi in one wavelength, but their relative phase, which is this term, accumulates phase twice as fast because one of them is going this way and one of them is going this way. So this is half of the wavelength. And this is a quarter of the wavelength. And the spacing between voltage maxima and minima is always a quarter wavelength. If I drew the current standing wave, it would have the opposite shape, which kind of makes sense. This is a short circuit, so you would expect to have a current maximum here and a current minimum at, you end up with a current minimum at the voltage maximum. So current is off by a quarter wavelength from voltage. Maxima show up where the minima are and vice versa. Any questions about this stuff?